Okay, good morning. Let us get started from where we left last time. So, we were discussing about resource sharing among tasks, real time tasks, and we examined what kind of problems that might arise. We saw the basic problem of priority inversion and then the unbounded priority inversion, and we had seen the simple protocol, the priority inheritance mechanism, the basic mechanism for supporting resource sharing among real time tasks. So, let us proceed from that point onwards. So, today we will look at highest locker protocol and the priority ceiling protocols. Let us first look at the basic idea behind the highest locker protocol. So, here the resources have a ceiling priority value assigned to them, and the ceiling priority value of a resource is the highest priority of all tasks needing to use that resource. So, we know beforehand what are the tasks that would be using a resource, and then set the ceiling priority of that resource equal to the highest of the task priorities that are going to use the resource. And then whenever a task acquires a resource, its priority value is automatically raised to the ceiling priority of that resource. If it acquires multiple resources, then it will be naturally the highest of all these priorities. So, that is the basic mechanism, and we will see that it addresses the shortcomings of the basic inheritance scheme. We had identified the basic problems of the inheritance scheme. Does anybody remember what are the basic? Yeah. So, there are possibility of deadlock and chain blocking. Yes. So, let us see how it will overcome those problems, and unfortunately, the highest locker protocol introduces new problems, and therefore, highest locker protocol by itself is not used, but it gives us the basic understanding based on which we can develop the ceiling protocol, the priority ceiling protocol, which is the one which is actually used. So, if we understand the highest locker protocol, we will understand what are the issues that the priority ceiling protocol is required to address, and therefore, why certain clauses etc. are added there. So, let us look at that. So, during the design of the system, the ceiling priority is assigned to all critical resources, and the priority is equal to the highest priority of all tasks that might use the resource. And when the task acquires the resource, its priority raised to the ceiling priority. So, this is the situation where resource R is being used by tasks T1, T2, T3. So, R will be associated with a ceiling R, which is the maximum priority of T1, T2, T3. Just an example, if we have priority of T1 is 5 and the priority of T3 is 8 and priority of T2 is 2, and assume that the lower the priority value, the higher is the priority, let us assume that, and then the maximum priority will be 2 and the ceiling value associated with R will be 2. So, whenever a task acquires R, if T3 acquires R, its priority will become 2, right. But one thing we need to remember that for Windows, the higher priority values indicate higher priorities, whereas in Unix it is just the other way around. The lower priority values like 2 is higher priority than 8, here 8 will be higher priority than 2. So, let us just remember that what kind of, because conventions are different for different operating systems. So, we need to appropriately select the priority value. Now, as soon as the task acquires the resource, its priority is raised to the ceiling value, and we will see that this simple mechanism will help eliminate the unbounded priority inversions, the deadlock and the chain blocking. But it would introduce a new problem which we will call as the inheritance blocking. So, this is an example of the working of the algorithm. T1, T2, T3 are sharing the resource R. The ceiling value associated with R is 2, because these have priorities 5 to 8 and the maximum of this is 2. Now, let us say T1 acquires R, T1's own priority is 5, and as soon as it requires R, its priority would become 2. And if T2 gets ready by that time, and then it would have to wait. But the thing is that the intermediate priority tasks, so there is an inversion occurring no doubt here, let us see here that the task 5 priority has become 2, it is executing, whereas T2 whose priority is 2 is waiting, but the thing is that unbounded priority inversions are avoided. So, T4 does not need any resource, cannot preempt T1 from CPU uses, because T1's priority has become more. Similarly, T5. Now, let us look at a theorem. When highest locker protocol is used for resource sharing, once a task gets any one of the resource, it will not block any further, or in other words, there is no chain blocking. This theorem says that under highest locker protocol there is no chain blocking. So, we will just look at the outline of the proof, very simple. We can argue out that there will not be any chain blocking, and then we will look at two corollaries of this theorem. That is, once a task is granted a resource, all resources required by it must be free. So, when a task is granted one resource under HLP, then none of the resources could have been held by any other task. That is a corollary, because no, it does not block any further. From here we can easily show that if a task gets one resource, then other resources must be free at that time. And the other corollary is that I cannot undergo chain blocking. So, let us see the outline of the proof for why there cannot be any chain blocking, and once it gets a resource, one resource, then it will not be blocked any further. So, I do not have a slide for that, I will just outline the proof on the paper. So, just observe simple concept. See, let us assume we will prove it by contradiction. So, let us assume that there are two tasks who are holding resources R1 and R2, and let us say we have a higher priority task. So, let us say this is T1, T2 and T3. Let us assume T3 is higher priority, that way the priority inheritance, the priority inversion will occur. Now, let us say T3, so as soon as T1 acquires R1, its resource its priority will be raised to the ceiling priority value, is not it? That is the basic protocol. So, according to this scheme, the resource R1 is required by T1 and T3, right. Similarly, resource R2 is required by T2 and T3, sorry, you need to show it, we are showing it as rectangle. So, let us follow that convention. So, R2, the resource R2 is required by T2 and T3, is not it. So, the ceiling priority of R1, let us assign some arbitrary priority value just for our understanding. we can show it for any arbitrary priorities. So, let us assume that its priority is let us say some 5, its priority is 8 and its priority is let us say 2. Now, the ceiling priority of R 2 will be how much? Maximum of 2 and 8, is not it, 2 and 8, because R 2 is used by T 2 and T 3. So, the ceiling of R 2 will be 2, is not it. Similarly, the ceiling of R 1 will be 2, will be at least 2, because there might be other tasks which might be using whose priority might be 1. So, its priority is at least 2. Now, let us assume that T 2 first blocks for resource T 3 first blocks for resource R 1 and then it gets the resource and then computes, and by that time T 2 is holding R 2 and then it again, as it requires R 2, it again blocks. Let us assume this and we will show that it is not possible. So, when T 1 acquires R 1, its priority must have been set to 2, right. And if its priority was set to 2, then it is not possible that another task can acquire a resource R 2, because it is a lower priority task to acquire R 2, because it is already a higher priority. Its priority has already increased to 2 after acquiring the resource, is not it. So, as soon as its priority would have acquired the resource, its priority would have got raised to 2, there is no chance that T 2 could have acquired R 2. Similarly, we can show that if T 2 started executing and acquired R 2, R 1 could not have possibly been acquired by R 1, sorry, R 1 could not have possibly been acquired by T 1. Yes, two different resources. Let us just please understand again, I am just repeating that resource R 1, the ceiling value is 2, and by the highest Locker protocol, as soon as any task acquires that resource, its priority automatically becomes 2, right. Now, similar is the case with R 2, sorry R 1, as soon as a task acquires R 1, its priority will become 2, right. Now, we are assuming that the situation exists where R 1 is held by some task, the task T 1, its priority was 5, and R 2 was is being held by T 2, whose priority is 8, right. But let us assume that first R 1 was holding sorry T 1 was holding R 1, then T 1's priority will be raised to 2, it's high priority. So, at that time it is not possible that T 2 can execute, because T 2 is a lower priority. Unless a higher priority task completes, how will it get chance to execute, right. It has got its resource, it is executing. So, T 2 could not have possibly executed and acquired R 2, and similarly we can argue that if T 2 had first acquired R 2, T 2 started executing and first acquired R 2, T 2's priority would have increased to 2, and T 1 being a priority 5 could not have executed and got the resource R 1. Now, we can show through a similar argument. So, this is a contradiction basically.
It may be the case that T 1 the ceiling priority of R 1 is say 5.
R 1 should see R 1 should be ceiling priority R 1 should be at least as much as T 3, which is the high priority task.
Suppose this is also 5.
Yes.
Then the ceiling priority will be 5.
Suppose this is 5, is it?
Yes,
yeah, right.
Then the
Ceiling priority is 5. Okay. So, these two are equal priority you are saying, right. So, this is T1 and T3 are 5. Okay.
And say suppose T2's priority is 4.
T2's priority is 4. Okay. So, its priority will be 4. Yes.
R R1 started executing, so T1 started executing first.
T1 started executing first, yes,
It has acquired R1
yes,
and its priority is still 5.
yes, okay,
But now T2 has come.
yes,
T2's priority is 4.
4, yes, T2's priority will be made 4, yes,
Yes. So T2 has to execute.
T2 will execute and complete, yes.
Yes, sir. It will preempt T1.
It will preempt T1 and then T2 will start executing and T2 will complete.
R2.
Yeah, it would have acquired R2 and then it will complete, because T3's priority is 5. So, T3 cannot execute, right. 4 is a higher priority, T2 has priority has become 4. So, T2's priority, T2 would complete before T3 can get a chance to execute. So, we can construct all possible scenarios and see that this holds, and we can prove it actually formally by considering all possible values of priority combinations ij. In terms of ij we can prove, which is worked out in the book. And we can also show through a very similar argument that if a task is holding both the resources, that is also a possibility, that a task T1 was holding both R1 and R2, right, and then T2, which is a higher priority task, let us say T2's priority is 2 and T1's priority is let us say 5. So, T1 was holding both R1 and R2 and T2 was blocking on R1, right. Now, let us say T1, so first time it has blocked for R1 and then after some time T1 completed using R1 and then T2 started executing and again it blocked for R2 because it also needed R2. So, again it started blocking for R2. So, 2 times it has blocked, but that is also not possible, exactly, that is not possible, because as long as it is holding some resource R2 which is required by T2, any resource required by T2, its priority will become at least as much as this, right. So, unless it releases both these resources, it completes execution of both these resources, T2 will not get a chance to execute, right. So, once it gets one of its resource, it will not block any further for any other resource, or in other words, chain blocking is not possible under highest locker protocol. So, you can try with more examples and then look at the formal proof. See that the proof outline is just similar, excepting that we just generalize, instead of taking instances 5, 2 etcetera, we just generalize that, right. Or if you find a better proof, easier proof, just report it to me, we will consider that for a bonus mark. So, let us now proceed. So, we know that under highest locker protocol, chain blocking is not possible, and once it gets one resource, other resources must be available. So, this much we know. Now, we have seen that it avoids unbounded priority inversion. We can easily show that it prevents deadlock by the corollary 1. From corollary 1, where we said that, see, once it gets one resource, other resources must be free, right. So, based on that, we can show that there cannot be a deadlock, because it has got one resource, all other resources are free. So, where is the chance of deadlock? We can even show that through some examples. See, this is the example where the basic inheritance scheme was getting into deadlock, right. So, let us say T1 and T2 are 2 tasks requiring resources R1 and R2, and let us say T2 is a lower priority, T1 is a higher priority, and let us say T2 started executing, locked R2, and then T1 started executing and issued a command lock R1, but that is not possible, because as soon as T2 has acquired R2, the ceiling priority of R2 must be as much as the priority of T1, and therefore, this assumption that it will lock R1 is not possible, right. So, deadlock is prevented. Now, the main problem of the highest locker protocol is the inheritance related inversion or inheritance blocking. So, here when a low priority task gets a resource, its priority is raised to high values, and then the tasks whose priority is more than this low priority task, which are the intermediate priority tasks, even though they do not need any resource, they will be prevented from execution because the low priority task's priority has increased, right. So, this is called as the inheritance blocking. So, this is just an example of a inheritance blocking. We have these 3 tasks with priority 5 to 8. So, the ceiling priority of the resource is 2. Now, let us say T1 whose priority is 5 acquired R, priority becomes 2 by the highest locker protocol, and then T3 priority is 4, it is more than T1, cannot execute even though it is ready, cannot execute. Okay. So, right. So, we should make right, there is a problem here, we should have named this task as T4 or T5 something, right, because T3's priority is 8, that is correct. So, it should be T4 or T5 something whose priority is 4 cannot execute. So, it is undergoing inheritance related inversion. Similarly, T5 its priority is 3 cannot execute because its priority has become 2. So, these tasks are undergoing inheritance inversion until T1 completes. So, what is the duration for which T3 and T5 might undergo inheritance inversion? Yes. So, the duration for which T1 needs the resource R, that is the duration for which T3 and T5 will undergo inheritance inversion.
So, like if T1 blocks for input output or something?
If it blocks for input output, then the situation is more complex. We need to modify our simple assumption, right. The duration we need to calculate accordingly, but right now we are assuming that once it gets the resource, it continues without blocking, right. Okay. Now, because of the inheritance related inversion, it is rarely used in applications, because just imagine the lowest priority task, there is a chance that it becomes the highest priority task and then it blocks everything else. For example, a logging task which just keeps the logs, it can become the highest priority task and even the most sensitive tasks will be blocked. And since this can occur for many low priority tasks, rarely used in real applications. So, the problems of the highest locker protocol is overcome by the ceiling protocol, the priority ceiling protocol. So, it is an extension of the highest locker protocol, and we now know the drawbacks of the basic inheritance scheme, even though it avoided the unbounded inversion and deadlock and chain blocking, and the highest locker protocol, it overcame the deadlock and the chain blocking problem, but it had a new problem, the inheritance related inversion. So, let us see how the priority ceiling protocol overcomes that. Here, just like the highest locker protocol, a ceiling priority is computed for every resource, but in the highest locker protocol, whenever a resource was acquired by a task, its priority was raised to the ceiling value. Here it does not occur like that. Here we have a operating system variable which denotes the highest ceiling of all logged semaphores. So, if R1, R2 are two resources that are being used and they have ceiling value of C1 and C2, then the operating system variable will get maximum of C1 and C2. So, the operating system variable, which we will call as the current system ceiling or CSC, it stores the highest of all ceiling protocols of the resources under use.
Ceiling of semaphore, what does that mean? Ceiling of semaphore.
Logged semaphore, see the terms that are used here, like we sometimes will call it as mutex, logged mutex, called logged semaphore, logged resource. So, these are terminologies we will just keep using equivalently.
So semaphore will have a value.
Yes,
1, 2, minus 1, minus 2.
exactly.
And the priority is different thing again. The ceiling of the semaphore value or the priority value is being stored.
No, no, this is a logged semaphore, and logged semaphore is the semaphore is set, right. And we instead of saying that the ceiling is associated with a resource, we just used it as ceiling is associated with a semaphore,
Actually,
right, because a semaphore,
highest of all the priorities means ceiling priorities.
exactly, that is all, highest of all ceiling priorities of various logged resources. So, that is the terminology we are using so far. So, possibly because we just used logged semaphore. So, maybe that is the causing the confusion, but these are some of the terms that are used interchangeably, right. Okay, let us proceed. But what is an operating system variable? I mean, how do you check the operating, let us say you have, all of you have used Unix. So, how do you check what are the current environment, the system, the set of system variables is called as the environment variables, right.
Echo dollar variable.
Yeah.
Dollar of path.
Path, no, path is just one example. Path is a environment variable, it is a system variable, the current path. But how do you check all the environment variables that are there?
Profile. They, like all the variables that are set in a file.
Anyone wants to give, see all of you have used Unix, how do you check the environment variables?
For seeing this semaphores.
No, no, see as operating system to function, see operating system is configurable, no, the path can be changed, the current path, you do not have to set the path each time, right. Or no, Linux you have used all, no, Unix you have used. So, what is the command for Unix? env, if you give a command env, you will see the set of environment variables, just try that out. It will list at least 2 dozens of variables, just check what are the variables, why they are used. So, the priority inheritance protocol is basically a greedy approach, because whenever a request to a resource is made, as long as the resource is available, it will be allocated. See, if it is being used by some task, then it might block, and then the inheritance scheme applies and so on. But as long as the resource is there and some task requests it, it gets it, is not it. So, that is a greedy approach, but here we will see that in the priority ceiling protocol, a resource may be there, free resource, but the task will be prevented from acquiring it. So, it is not a greedy approach. Later I will just observe as we go through the ceiling protocol, just observe why it is not a greedy approach, and later I will just ask you a question, just give us an example why the ceiling protocol is not a greedy approach. So, the current system ceiling, as we were saying, is set to the maximum of all ceiling values of the resources in use. This is just a formal writing that the system, the current system ceiling is equal to the maximum of all ceiling values of resources that are currently in use. And to start with, the current system ceiling is initialized to 0 because no resources are being used, assuming that 0 means that nothing is being used, or we can even set it to a very large value, depends on the kind of convention we are following. So, the priority ceiling protocol basically has 2 rules. One is the resource grant rule and the resource release rule. Actually, it should have been release, mistake here, grant rule and the release rule. So, first let us look at the grant rule. The grant rule has two clauses here. So, when a resource is to be granted, first the request occurs and then there is a inheritance clause that is applied. So, let us first concentrate on the grant rule and then we will look at the release rule. So, here unless a task holds a resource that set the current system ceiling, it cannot lock a resource unless its priority is more than the current system ceiling. So, let us assume, I will just I do not think there is example here, I will just take an example. See, this is one of the very basic working of the ceiling protocol. So, I will just read the statement once again, then I will just give you an example. Unless a task holds a resource that set the current system ceiling, it can lock a resource only if its priority is greater than the CSC, the current system ceiling. So, let us say we have a situation where we have a task which needs two resources R1 and R2. R1 and R2 are needed by T1 and let us say the R1 is also used by T2 . So, T1's priority let us say 5 and T2's priority let us say 2. So, the ceiling priority of R1 will become 2, is not it. Now, R2 let us say is being used by T1 and also T3 and T1's priority is 5 and T3's priority is let us say 3 or maybe you can consider 8 or something. So, R2's ceiling priority, so C1 is 2 and here C1 is equal to 3, right. Now, let us say T1 first acquired R2. So, the current system ceiling will be set to 2, no sorry it will be set to 3. So, T1 first acquired R2 and R2's ceiling priority, sorry this C2, R2's ceiling priority is 3. So, the current system ceiling will be made 3. Now, after some time T1 wanted to lock R1 and then it will be directly granted access to R1, the current system ceiling will not be looked at, it will because it is the one which had set the current system ceiling. The CSC is not a consequence for T1, but let us say we have the task T2 let us say another task, let me just give R3 which is being used by T5. So, T5 if it requests R3, its current its priority will be checked, T5's priority will be checked with the current system ceiling and if its priority is less than the current system ceiling, it will be prevented from acquiring the resource that it needs. And let us say just to explain it little bit further, let us just rather than complicating with R3, let us just assume that T2 whose priority is 2 also needs R2. Okay, I think that will. So, T2's priority is 2. So, R2's ceiling will become 2, right, maximum of all these priorities. Now, let us say T 1 first acquired R 2, its priority will become 2.
So the CSC will become
Sorry, not the CSC will become 2. The priorities do not change, the priority of T 1 do not change. Please remember that under CSC the priority does not change upon acquiring a resource, unlike the highest lacquer protocol. So, only the current system ceiling is set to 2, and let us say T 1 sorry T 3 wants to acquire R 2, because its priority was not increased, T 1's priority was not increased by acquiring R 2, let us say T 3 started executing, because its priority is 3, and after some time it wanted to use resource R 2, then T 3's priority will be checked against 2, it is higher priority than 3. So, T 3 will be prevented from locking. Is that okay, or need to explain with another example? Anybody thinks it is slightly more complex, so that we need to take one more example? Yes? Okay, let me just take another example just to explain this resource request clause in the grant procedure. So, let us say we have a resource R 1, and the resource R 1 is needed by 3 tasks. Let me just write T 1, T 2 and T 3, and let us give some arbitrary priority values 5, 7, 3, or you can give some values to me, I can write that. So, the ceiling value of R 1 will be how much? 3. C 1, the ceiling associated with R 1 will be 3. Now, as soon as any task here acquires the resource, the current system ceiling will be set to the ceiling value here. So, CSC will be made 3, let us say T 2 has acquired the resource, but T 2's priority does not change, it is only the environment variable which has got changed. Now, it is possible that another task T 4, whose priority is let us say 2 or something, or let us say 4, it will start executing, because its priority is more than T 2, right. So, let us say T 2 has acquired R 1 and T 2's priority has not changed, T 2 has acquired R 1 and the current system ceiling is set to 3, and T 4 priority 4 more than 7, T 4 starts executing, right. Now, let us consider the example where T 4 also needs resource, let us say R 2, and T 4 requests for R 2, then T 4's priority will be checked with current system ceiling, and then if T 4's priority is larger than the current system ceiling, it will be granted R 2, but it is not, here the priority is only 4. So, it will be prevented from locking R 2.
if T 4 requests R 1 and if T 4's priority is greater than CSC, in that case.
No, if T 4 requests R 1, we have to write T 4 first and its ceiling priority will become 4, right. So, can you just imagine or think why this clause is required, checking against the current system ceiling, and see here the resource was idle, no one is needing that resource, but still T 4 is prevented from getting R 2. Can you think why this clause is introduced in the ceiling protocol?
So that all the resources don't get like are available at a time, like if
Okay.
it does not get blocked. If one
Exactly. See here the basic idea here, like he said, see the basic idea is that intermediate priority tasks are not blocked. They are allowed to execute, unlike the basic the highest locker protocol, where these tasks were undergoing inheritance related inversion. Here they do not undergo inheritance related inversion, no priority inheritance is applied till now. It is only the current system ceiling is changed, but the thing is that any related resource that it might need should be available, otherwise there will be problem of deadlock, chain blocking, all those problems will come, and to overcome those problems the current system ceiling is set. But there is a possibility that R2 is never needed by T2, but still T4 is prevented from accessing it. So, that we will call as a problem here, we will call it as some avoidance related inversion later, but this problem can arise that some resource is never going to be required by anybody excepting this task and some other task T7, but still they are blocked. These are shared resources basically. So, I have written T4, T7 which are unrelated to this, and this never needs this resource, but still they will be prevented unless this has a priority 1, T4's priority is 1, and if its T4's priority is 1, then we know that T1 is never going to need a resource whose priority is 1, whose ceiling priority is 1, and therefore, T4 will be allowed to execute R2, right. So, this will prevent the deadlock and T4 will execute and complete. So, let us see the other clauses. Yes.
One more problem in these protocols is that we need to statically calculate the CSC value, right? Priorly only we need to determine what all the tasks use this resource. Dynamically a task cannot request any resource. Right?
Of course, see any embedded real time system, we will know what are the resources required by a task. It is not that dynamically they request resources, does not happen. We should know that what exactly is the data structures, what are the devices etc. used by a resource beforehand. For any dynamic requests are not allowed, that see some device has been added and then how to use it etc., that will create problem, or some new task which has a new resource data structure, how to access. No, these are all statically decided during design time, what are going to be the tasks and resources. Now, let us proceed with the other clauses here. So, the first one was the request clause, and we saw that unless a task holds a resource that set the current system ceiling, it will be prevented from locking any resource except when its priority is greater than CSC. Now, the request, sorry.
That point left that thing. If it has a resource which sets the system ceiling,
Yes.
then it can acquire any resource.
Exactly. If it has set the system ceiling, then any request by it will not be checked against CSC. It can lock any request that it needs. So, let us look at the resource request clause more formally. So, we can say that if a task is holding a resource whose ceiling priority equals the CSC, I mean that is the task which had set the CSC, then the task is granted access to the resource. Otherwise, Ti is not granted some requested CRJ unless the priority of Ti, sorry Tj it should have been, no Ti is otherwise, yeah, otherwise Ti is not granted the resource unless the priority of Ti is greater than CSC. Whatever we said, just written slightly in the pseudocode form, right. Now, in both A and B, if Ti is granted access to the resource, then CSC is set to the ceiling CRJ. So, whatever is the maximum ceiling value, the CSC gets changed. As soon as there is a resource allocation, the ceiling value will, the CSC will get updated. because CSC will keep track of the highest ceiling value, that is of the resource currently in use, right. So, whenever we grant a resource, we have to change the CSC if required.
Sir, CSC can decrease in a course of time.
Yes, when there is a release of resource, it will decrease. So, that also, that clause we will see. Right now, we are just looking at the grant clause, then we will look at the release clause. Okay. Now, let us look at the second clause in the grant scheme, that is the inheritance clause. If a task is prevented from locking a resource, it had requested some resource, but it is prevented, and then the inheritance clause applies. The task holding the resource will inherit the priority of the blocked task. So, let us look at the example that we are constructing. So, the first example we had constructed is I think this one, where we had said that see three tasks are there, and they are there are two resources R1 and R2, and T1 requested R2 and CSC is set to 2. Now, let us say T2 requests R1 at that time, then T2 will get blocked. T2 has started, was ready, and then T2 is blocked just because the resource is not available, and then the priority of T1 will be raised to 2 by the inheritance clause, right. So, just listen to the scenario again. T1 started executing, priority is 5, and then acquired the resource R2. Once it acquired the resource R2, its priority did not change, it is still priority 5, but the only thing that changed was the CSC value was set to 2. Now, T2, because its priority 2, it started executing. As soon as it became ready, it started executing, preempted T1, the low priority task, started executing. After some time, it needed R1. Okay, yeah, T2, it needed R1, sorry, R2. Okay, does not matter if whether it is R1 or R2.
Shouldn't it be on the same resource?
No, not necessary. It can be any resource. I hope that point is clear, that any resource request is governed by that rule. So, T2 may request R1 also. So, let us say T2 requested R1, and then this request, the way it will be handled is, because it is not the one which set the system ceiling, it was set by T1. So, T2's priority will be checked against current system ceiling already 2. So, CSC will block, sorry, the T2 will block, its priority is not greater than CSC. So, T2 cannot acquire R1 and it will block, and when it blocks, T1's priority will get increased by the inheritance clause. Is that okay? So, whenever a higher priority task, see initially when it acquired a resource, its priority does not change, only the CSC value changes, and whenever any other task is prevented from acquiring any resource and is blocks, then the task that was holding the resource priority increases by the inheritance clause.
The task that is blocked has got lower priority in that case?
Then nothing will happen. See, inheritance clause applies only when the priority is the blocked task has a higher priority than the task that is executing. See, if it was a lower priority, then even this situation will not arise, like it started executing and then requested resource, that scenario will not exist at all. So, we are talking of only higher priority task requesting a resource. So, let us look at some of the features of the priority ceiling protocol, look at one example, and then we will look at the release clause. So, as we have already seen that a task, when it gets a resource, its priority does not change. It does not become the ceiling priority like it used to happen in the highest lacquer protocol. In fact, it does not change at all. Only when a higher priority task waits for being denied a resource, then the inheritance clause is applied. So, we will see that this simple scheme, not as simple as the highest lacquer, slightly more complex, because we have a system variable which is set, and when a resource is requested, there are two clauses. One is the request clause where it checks against the ceiling priority, and then if it is the task which had set the CSC, then it is not checked against CSC. So, and then the inheritance clause. We will see that this will prevent the deadlock situation, it will prevent chain blocking, it will prevent unbounded priority inversion, and it will reduce the inheritance related inversion to a large extent. Cannot say that totally eliminated, inheritance related inversion will still be there, but substantially reduced. So, let us look at this.
Sir,
Yes, please.
previous 2 slides. One more.
This one, inheritance clause.
Sorry, what
Yeah.
is the use of this?
Why the inheritance clause is required? Is it?
Yes.
Okay. So, his question is why inheritance clause is required. Can anybody answer this question? Why do we need the inheritance clause?
Is it for unbounded?
Exactly. Exactly. See, unless we have the inheritance clause, the task whose priority is higher, right, it will just intermediate priority tasks will keep executing, and the higher priority task which is waiting will keep on waiting. That is unbounded priority inversion. So, the inheritance clause is there to prevent unbounded priority inversion, but it is not really raised to ceiling priority, but to the priority of the task that is waiting for the resource. So, without inheritance clause there will be unbounded priority inversion. Is that okay? Now, let us proceed further. There is the resource release clause also. When a resource is released by a task which was holding the ceiling, then if this was the maximum of all ceilings that are of the resources currently in use, maximum ceiling of all resources that are currently in use, then the CSC is changed to the one that is current maximum. If it is not the maximum, then nothing changes, it just releases the resource. And of course, if it had inherited a priority, if the inheritance clause is applied, then that also needs to be reversed, is not it? So, if inheritance clause was applied, then it will revert to its original priority. If it is not holding any resource, if it is holding some other resource, then of course, it will get the highest priority of all the blocked tasks on those resources. So, just the opposite of the resource release, resource grant clause. Here the CSC value will get updated if applicable, and it will revert to its old priority if applicable, right. So, we will just stop here, and we will just take a break and meet for the next class.